The Hubble Space Telescope has just made a discovery that is shaking the foundations of astronomy. Deep inside the interstellar object known as 3I Atlas, scientists have detected a massive structure that should not exist, not by any known model of space physics. This isn't a rumour, this isn't speculation. These are real observations from one of the most powerful space telescopes ever built. The size, position, and internal formation of this structure defy everything scientists expected to find. Astronomers are now questioning long-held assumptions about interstellar objects, and even the limits of how matter behaves in deep space. In this video, you'll see what Hubble actually observed, why this discovery is causing intense debate among experts, and how 3I Atlas may represent something entirely new and potentially unprecedented. Watch until the end, because the final detail of this discovery is the one scientists admit they cannot fully explain, and it may force a complete rethink of what we believe exists beyond our solar system. When the Hubble Space Telescope was first scheduled to re-image 3I Atlas in early January, astronomers weren't expecting much. By now they assumed the interstellar object would be further degraded, just another cloud of debris trailing behind a fast-dissolving core. That's what comets do after perihelion. They crumble, they scatter light, they blur at the edges, especially when they've been exposed to solar radiation, tidal pressure, and the violent gradients that come from moving through magnetic storms near the Sun. So the schedule was routine, just another pass, just more coma and tail analysis. But what they saw instead changed the entire conversation. The first high-resolution stat came in at 0316 UTC, captured through Hubble's WFC3 ultraviolet channel. And it didn't show dust diffusion, it didn't show disintegration, it showed edges, clear, geometrically consistent edges. At first, the operators flagged it as a likely artifact. These things happen. Cosmic ray hits, sensor bleed, software glitches in the image stacking pipeline. They can all produce sharp lines where there should be none. So they ran the filters again. They scrubbed the data. They realigned the light curves to account for any known diffraction from nearby objects. But when the raw channels were overlaid and compared across the full sweep, ultraviolet, visible, near IR, the structure remained. It wasn't a glitch. It wasn't noise. It was real. The core of 3I Atlas, previously thought to be fragmenting, appeared intact, and not only intact but outlined. There were parallel ridges, almost struts, running along the longitudinal axis. There was a pronounced shadowed cavity near the midsection, and flanking it were two symmetrical masses that curved inward like stabilizing arms. No natural comet or asteroid has ever shown such internal definition. Not under this kind of stress, not at this level of exposure. Even more troubling, the contrast persisted as Hubble changed filters. In visible light, the outline became even clearer. There were light dips and glow zones in patterns too sharp for venting. The geometry wasn't chaotic, it was deliberate. One observer, a systems engineer at ESA reviewing the frames in real time, simply wrote in the margin, "This doesn't look broken. It looks manufactured." Within 12 hours, 3 other observatories, including a polarimetric ground array in Chile, confirmed that the object's internal contrast zones were not processing illusions. These were reflective differentials, that is to say, surfaces catching light at repeatable angles, consistent with a rigid frame. The reflection pattern changed as the object rotated, but the edges stayed in sync. This wasn't an ice shelf. This wasn't venting through a porous crust. This was a structure. That word doesn't appear lightly in scientific reports. It implies purpose, intent, or at the very least, pattern beyond accident. But here, structure became unavoidable, because the outline didn't fragment. It didn't dissolve across wavelengths. It didn't smudge with heat distortion. It remained every time the light changed. Even more disturbing was the size-to-shape ratio. Based on Hubble's angle of observation, the central void, the darkened notch that appeared between the ridges, was nearly uniform across 3 frames taken 2 hours apart. That implies internal cohesion. No comet should have a notch that clean, and certainly not one still radiating energy. As the analysis continued, something became clear. This wasn't just a core, it was a framework inside the core, a shape within the shape, a stable zone holding firm against the collapse surrounding it. And it shouldn't be there, not in an interstellar object, not after a solar encounter, not at all. In nature, symmetry is rare, especially in space. It exists, but only under very specific conditions. Crystalline growth, binary stars, hexagonal convection cells on Saturn's pole. But comets? Comets are chaos. They are built from collapse, assembled in the outer disks of newborn star systems from irregular collisions, frozen clumps, and turbulent fractures. Their shapes tell the story of violence, randomness, and time. That's why what Hubble detected inside 3I Atlas has left scientists stunned, because this isn't just an object with strange internal structure. It's an object with symmetry, and that's not supposed to happen. The first time the contrast data from the inner core was processed, what stood out wasn't just the presence of straight lines or cavities, it was the mirroring. Two ridges, equidistant from a central axis. A deep shadowed region, perfectly flanked. Variations in reflected light that rose and fell in predictable intervals across the object's surface. You don't get that in natural outgassing. You don't get that from a tumbling, eroding nucleus that's been bombarded by radiation, dust impacts, and internal sublimation. But here, in every band of light, the pattern repeated. At first, researchers thought it might be a trick of rotation, a visual effect caused by lighting angle or sensor bias. So they ran the scan in reverse. They simulated dozens of rotations and light vectors, and still the symmetry held. It wasn't an illusion, it was built into the object. Now let's be clear. Comets sometimes form bilobate shapes. Think of Comet 67P Churyumov-Gerasimenko, which looks like a rubber duck, two lobes connected by a narrow neck. That happens when two icy bodies collide slowly enough to fuse. But 3I Atlas isn't bilobate. It's not even close. It's not a snowman. It's a central structure with symmetrical internal features. Not just two masses stuck together. The lines aren't bulbous. They're geometric, linear, aligned, like beams or compartments. When scientists mapped the observed reflectivity across the visible and IR bands, they found that the angles of light bounce were matched across opposing quadrants. This shouldn't be possible. Surface dust should scatter asymmetrically, especially if one side of the object is more eroded or more exposed to solar heating. But in this case, both sides behaved the same, not in absolute intensity, but in structure. Peaks and valleys in the reflectivity graph occurred at equal offsets. It was like watching a mechanical object roll through space with its own quiet order. And that's what set the alarms off, because this isn't the kind of object that forms in a protoplanetary disk, not this way. Not with that kind of mirrored internal rhythm. The moment a comet is born, in the cold outer reaches of its star system, it's battered. It never has a chance to grow clean lines. Even if some symmetrical shape emerged by chance, solar radiation, outgassing, and orbital stress would distort it. Nature doesn't preserve symmetry under heat. It shatters it. But not here. The deeper Hubble looked, the more unnatural the structure seemed. Not because it was shaped like a ship or looked like a machine, but because it was mathematically balanced. And nature doesn't do math like this in the middle of a comet. Some researchers have suggested that this might be a rare case of resonant erosion, a process where internal materials sublimate in a way that exaggerates pre-existing flaws into mirrored cavities. But that theory requires a level of structural regularity to begin with. And 3I Atlas came from deep interstellar space. It's been bombarded by cosmic rays for possibly millions of years. Any flaws it had should have been shattered by now, not sharpened. The symmetry here isn't a scar, it's a feature still holding its shape, still reflecting light the same way, still ignoring the laws that comets are supposed to follow. And somewhere in the silence of that pattern, a question begins to echo. What kind of object survives chaos by being symmetrical? When Hubble's images of 3I Atlas were first examined, the internal structure was what caught most eyes, the ridges, the cavity, the unnatural symmetry. But it wasn't just what was inside that raised questions, it was what was wrapped around it. Faint at first. Faint enough to miss in raw resolution scans, but unmistakable once the filters were aligned. A soft, bluish envelope, not a glow, not a tail, but a field, barely visible, pulsing like a sheath of energy. To the untrained eye, it might have looked like residual gas or refracted starlight. But the wavelength was off. The field didn't scatter like coma particles. It didn't drift outward like sublimated ice or solar wind dust. It clung, consistently, like a membrane, and it moved with the object, not behind it. not streaked in a tail, but surrounding the body like a shell. When astronomers pulled spectral data from the surrounding region, they found something unexpected. This wasn't standard ionization from ultraviolet light-striking gas. The field's spectral signature was narrower, cleaner, centered around the blue edge of the visible spectrum dipping into ultraviolet, a range more commonly associated with plasma sheath behavior, like that observed around spacecraft during atmospheric re-entry. This got the attention of physicists, because a plasma sheath requires something to ionize, a boundary between a surface and surrounding particles, like an electric barrier. And that raised a troubling question. What kind of comet sustains a plasma sheath? The answer? None. At least none we've ever seen. Comet tails can fluoresce, comas can become energized, but the fields are chaotic, turbulent, they ripple under solar pressure and magnetic interference. But this glow, this blue envelope, showed coherence. It pulsed faintly, at intervals measured by multiple ground observatories using UV photometry. The rhythm wasn't exact, but it was close enough to suggest a stabilizing mechanism, something damping the fluctuations, something holding the envelope in place. When researchers cross-referenced the pulse data with readings from the Parker Solar Probe, which was scanning the solar wind upstream at the time, they noticed a coinciding disturbance, a short-lived magnetic compression in the region 3I Atlas had just passed through. Not a flare, not a CME, just a brief, directional disturbance in the heliospheric current, like the solar wind had momentarily been bent. Now, that kind of event isn't unknown. Large bodies, even planets, can create magnetic shadows. But this wasn't a planet. This was an interstellar object, likely only a few kilometers across. And yet, the disturbance it left in its wake was disproportionate to its size. One explanation, however speculative, began to gain traction in closed academic channels. The possibility that the envelope surrounding 3 Atlas wasn't just a passive artifact of interaction with solar wind, but a response, a kind of buffering field, the way electromagnetic shielding can form around conductive structures when subjected to extreme radiation. That theory would imply something even more shocking, that the surface of the object is conductive. Natural comets aren't conductive. Their crusts are porous, dusty. Their cores are ice, rock, and volatile gas pockets. They don't hold charge. They don't stabilize fields. But 3I Atlas, for reasons still unexplained, does. The envelope also created another complication. In multiple long exposure frames, it reflected sunlight at specific angles, a soft shimmering halo with small vector shifts in brightness. Not consistent with tail flare or coma turbulence, it acted more like a lens, a soft barrier bending and reshaping incoming light. This observation raised a final chilling implication. What if the envelope is part of the structure? Not an after effect, but a system. One that actively manages radiation, modulates temperature, or controls energy flow around the object. If that's true, then what we're seeing is no longer passive reflection, it's shielding. And comets don't carry shields. There's a rhythm to how objects spin in space, a signature that reveals what's happening beneath their surfaces. For natural comets, that rotation is usually unstable, chaotic, and slowly degrading over time. They tumble, they precess. Their spin accelerates as jets erupt, throwing off angular momentum in random directions. That's normal. That's expected. But when researchers began plotting the internal rotation curve of 3I Atlas, the data said something very different. Because its spin didn't become more chaotic, it became more stable. Before its solar encounter, 3I Atlas exhibited what astronomers assumed was a typical rotational profile. The object's brightness oscillated as it spun, revealing asymmetries in shape and surface texture. These light curve variations are how scientists estimate rotation periods. In early October, the consensus was that the object rotated once every 11.2 hours, with minor irregularities indicating an uneven mass distribution. Again, typical for a comet that's been drifting through space for millions of years. But something changed after perihelion. Within 3 days of passing its closest point to the Sun, the object's light curve smoothed. The oscillations didn't disappear, but they narrowed. The peaks became more regular. The intervals between brightness variations stabilized. And when analysts recalculated the rotation period using perihelion data, they found something stunning. The spin had slowed down slightly, and the fluctuations had become more synchronized. In plain terms, the Recursive atlas started spinning like a balanced system. This is deeply problematic for natural models. Normally, a comet exposed to intense solar radiation experiences increased rotational instability. As ice is sublimate and jets fire from the surface, they act like tiny thrusters. They push the object unevenly, spin rates change, axis alignment drifts. Often, this causes fragmentation. The object tears itself apart. But in this case, the opposite occurred. The rotation became calmer, more uniform. It was as if the object absorbed its own instability and corrected for it. There's only one way that could happen in a natural object: internal damping. In theory, if a comet has a liquid or semi-liquid core, like a muddy interior, then energy can be distributed throughout the mass. But 3 Atlas is far too small and too cold to sustain a molten or fluid center. Its interior should be brittle, frozen, and fractured. And yet it behaved like an object with internal stabilization. When Hubble and Webb telescopes tracked the object's phase angles, they noted something else. The orientation of its spin axis didn't drift over time. From multiple observation points, Earth-based, orbital, Earth-rays and solar-aligned, the rotation vector appeared fixed. That's not possible unless some mechanism is preserving torque. One idea was that it had a countermass system, like a pair of dense internal sections rotating in opposite directions to cancel wobble. That happens in satellites. It happens in engineered drones and spacecraft. But it has never, in the history of astronomy, been observed in a comet. Another proposed explanation was mass redistribution, the idea that a collapse or internal shift after perihelion caused the weight to rebalance. But that theory runs into another issue. No structural deformation was detected. No fragment trails. No sudden dust surges. The shape didn't change, only the rotation curve did. That leaves a third possibility. One that few are willing to write down, but many are beginning to consider. What if the object is actively managing its own spin? In engineering, it's called attitude control, a way for spacecraft to stay pointed in a specific direction, either by using gyroscopes, thrusters, or momentum wheels, is not science fiction. We've done it. So the question becomes, has something else done it here? Because 3I Atlas didn't just survive the Sun, it adjusted after it. For decades, comets have been considered radio quiet. They don't emit, they don't transmit, and they certainly don't modulate. What little radio signature they do produce comes from the interaction between sunlight and the vaporized molecules in their tails. Faint, broad-band emissions like static hissing in the background. But when observatories began listening more closely to 3I Atlas, they picked up something they weren't prepared to hear. The first anomaly came from the Meerkat radio array in South Africa. On December 28th, while monitoring a nearby pulsar field, one of its instruments detected a narrowband burst from the direction of 3I Atlas. It wasn't strong, less than 1/10 of a Jansky, but it stood out from the background noise. The frequency, 157 ms, with a secondary harmonic at 314 ms. That's not a random interval. That's a clean harmonic doubling, the kind typically associated with resonance, reflection, or intentional signal generation. At first, researchers dismissed it as a terrestrial artifact, a glitch, perhaps, or interference from a ground-based radar. But as standard protocol demands, they checked for signal coincidence across other arrays, and that's when things became more serious. Within 48 hours, 2 other observatories, one in Australia, the other in Argentina, reported similar bursts. Each detection lasted no more than 0.3 seconds, but they were identical in structure, right down to the decay curve. The pattern wasn't chaotic. It had a beginning, a midpoint peak, and a sharp fall-off. There were no chirps, no modulations, just a pulse, brief and concentrated. This forced a reconsideration. Because radio bursts in space, especially those with structure, don't come from nowhere. They come from processes, physical, electrical, or mechanical. So scientists had to ask, what process inside or near 3I Atlas was capable of producing such clean, narrow-band emissions? It wasn't tail emission, it wasn't solar wind scattering, it wasn't lightning, and because comets don't produce lightning. The only plausible explanation left was reflection. That is, solar radiation or background radio waves bouncing off a conductive surface. But even that created problems. The strength and clarity of the signal implied that the reflection was coming not from loose dust or ionized gas, but from a coherent structure, one with consistent surface properties. In other words, something inside the object was reflecting or even shaping these frequencies. To test this, analysts overlaid the signal detections with the rotational period of 3i Atlas. What they found added another layer of strangeness. The bursts aligned within 30 seconds with a consistent rotational phase angle, as if the emissions were tied to a specific region of the core that rotated into view once every 11 hours. That level of synchronization isn't a product of coincidence. It implies that the signal, or at least its source, is geometrically fixed. The final piece came from the Very Large Array in New Mexico. On January 1st, it detected not just a single pulse, but a doublet. 2 short bursts spaced 1.6 seconds apart, with a decibel delta that indicated a pulse echo, the kind of signal you'd get if a radio wave bounced inside a cavity, then emerged slightly delayed. That made researchers pause, because a natural void, a crack or tunnel inside a comet, wouldn't reflect clean radio pulses. It would scatter them, absorb them, muffle them. The only way to get a clean pulse echo is if the interior surface is smooth, dense and partially conductive, like a chamber or a waveguide. And so, for the first time, scientists had to consider the unspoken possibility that 3i Atlas contains an internal cavity capable of reflecting and possibly generating structured radio emissions. Not a message, not a transmission, but a resonance. A pulse from something inside, and natural comets don't pulse. What startled scientists most wasn't just what the Hubble image revealed, but what it hid. Behind the shimmering lattice of the structure inside 3i Atlas, researchers noticed something far more subtle. Not an object, not a flare, but a pattern of shadow, cast not by the comet's dust, not by the nucleus, but by something deeper. Something that seemed to occlude starlight in a way that didn't align with any known structure in the image itself. At first, they thought it might be a lensing artifact, a digital smear caused by overlapping brightness and cosmic rays. But then it persisted, in different frames taken hours apart. This dark signature stayed in the same relative position, rotating gently with the object itself. And it wasn't uniform. That was the most disturbing part. The shape of the shadow fluctuated in what looked like rhythmic intervals, almost as if the structure wasn't static but moving, adjusting, breathing. Some described it as a hexagonal flower slowly folding and unfolding, its silhouette flickering in and out of contrast depending on the angle. Others compared it to an aperture, like a camera's iris, modulating the amount of energy or visibility inside the structure. But what could cause such a mechanism in something thought to be a comet? That's when an old paper resurfaced. A decades-old analysis of brightness curves in interstellar objects, long dismissed as speculative. It had proposed that under certain gravitational and magnetic conditions, objects might shield parts of their internal components from external radiation, not as a survival mechanism, but as a form of data management, a way to interact with light itself, to encode, decode, or even broadcast using shadow rather than signal. What if 3i Atlas wasn't hiding a payload? What if the structure was the payload, and the shadows were the language? Astronomers began layering Hubble's shadow data with radio observations taken days earlier, and that's when the pattern emerged. Each shift in the dark geometry inside the structure coincided with subtle radio anomalies, tiny fluctuations in frequency drift, always timed within a specific bandwidth, as if the structure wasn't just reflecting starlight, it was shaping it, controlling how it exited the object, maybe even using it. No known natural process could account for the regularity. Dust clouds disperse, ice scatters, plasma shifts erratically. But this was deliberate, composed, like a message scrawled not in words but in silhouette. Still, not everyone agreed. Some theorists argued it was simply a form of resonance shadowing, light being diffracted around magnetic nodes in the interior, creating interference patterns that appeared structured but were random in origin. Others insisted it was a trick of angle, an alignment fluke between comet, sun, and camera. But the Hubble team wasn't satisfied with dismissal. They ran it through one last test. They inverted the image, applied the same processing used on deep-field quasars, where weak gravitational lensing often reveals hidden mass. And there it was, a repeating outline, not symmetrical, not perfect, but real. A form that didn't belong in any cometary blueprint, a shape that echoed through each pass, slightly shifted, always distinct. The term they began using quietly behind the scenes, structured occlusion, and while they didn't say what they thought it was, they also didn't say what it wasn't. Because once you admit there's a shadow being cast from within a comet, and that it behaves like a moving geometry, you have to ask the question that no one wants to write down in a scientific journal. What kind of structure wants to hide inside light? And why is it hiding now? As the light from the Hubble Space Telescope filtered back to Earth on the morning of January 6th, scientists expected more detail, but nothing fundamentally different from the previous series of observations. Instead, what they saw stunned even the most seasoned astronomers. Inside 3I Atlas, the structure, already beyond explanation, had subtly changed. Its outer silhouette remained steady, but the internal symmetry had twisted. A central contour, previously thought to be stable and solid, now displayed a gentle spiral motion, not fast, not chaotic, but intentional, as if the mass inside was reacting, not to outside pressure or thermal effects, but to awareness or memory. This spiral wasn't just a rotation, it was a reconfiguration. Using enhanced 3D reconstruction models based on the multi-angle light scatter Hubble had captured, astrophysicists rendered a clear picture of the object's updated core. It now showed a torus-like band, an inner ring, tilting in opposition to the primary axis of the comet's spin. At first, it resembled a magnetic field shift, something like what happens in stars undergoing core collapse or magnetic reconnection events. But there was no solar flare, no internal nuclear engine, and no fragmentation signature around the tail. The motion was clean, contained, intelligent. Even more compelling, this movement had a timing pattern that correlated with previous gravitational lensing anomalies, recorded near the object a few weeks prior. If the ring's movement was acting like a stabilizer, or worse, a gyroscope, then it meant the structure was orienting itself, not randomly, but based on stimuli from its environment. That possibility unsettled everyone in the room, because if 3I Atlas was realigning, it was doing so for a reason, and if it could control internal torque, that meant it wasn't passively drifting, it was guiding. One theory came from a research team that had worked previously on anomalous spin-axis alignments in deep space probes. They proposed that the spiral ring wasn't mechanical, but instead something like a phase-shifted plasma shell, a boundary where energetic fields reconfigure under extreme magnetic constraints. But even that left open the core question: why now? Why had the core of 3 Atlas waited until this exact segment of its orbit, just past Earth, to undergo a structural shift? One group looked back at Jupiter, another looked ahead, toward the outer planets, and a third group looked inward, reviewing the heliospheric plasma maps to check if something inside the solar system had triggered the change. The data wasn't conclusive, but the motion inside the structure had a pacing that matched something strange detected by the Parker Solar Probe last week, a soft frequency pulse that had barely registered on traditional instruments. That pulse, which nobody could explain at the time, had now taken on new meaning. Could the internal shift be a response to a signal? And if so, was the signal external, or was it a reflex, a biological or artificial reaction from within? The internal spiral didn't show the randomness of natural collapse. It wasn't symmetrical in a gravitational sense, but it held a balance. That implied design. Not the kind that builds cities, but the kind that builds balance, the kind that corrects drift, that avoids spin destabilization, that prepares for something ahead. No one in the control room said the word aloud. But they were all thinking the same thing: navigation. Not in the way comets navigate space by orbiting gravity wells, but by responding to spatial intent, course correction, even alignment with an unknown objective. The contour shift told a story, and its message was simple but chilling. This structure inside 3I Atlas isn't finished moving. It's becoming something with direction, and maybe, just maybe, it knows exactly where it's going. At first, the Hubble team didn't even realize what they were looking at. The images pouring in on the morning of January 6th were strange, but not immediately alarming, until someone on the optics team ran a standard light curve analysis. That's when the panic quietly started. Because the structure inside 3I Atlas wasn't just reflecting light like a normal comet. It wasn't behaving like a dusty rock in space with an icy crust shimmering in sunlight. It was doing something else entirely. It was bending the light. And not in the way you'd expect from gravitational lensing, which is caused by massive objects warping space-time. This distortion didn't match those clean arcing signatures. What Hubble detected was subtler, stranger. The incoming light from background stars, usually straight lines when passing near a translucent gas or a dusty shell, was being diffracted at precise uneven angles, not warped, not blurred, but redirected, as if some kind of structured geometry was guiding the starlight around itself. What made this so unsettling was the precision. These weren't natural, chaotic disturbances. They formed a recurring grid, a kind of woven interference pattern, much like what you'd expect if you passed a beam of light through engineered slits or nanostructured surfaces. Hubble wasn't just capturing an image, it was capturing behavior. And that behavior pointed toward one uncomfortable word: intentionality. As the analysis deepened, scientists began to suspect they were looking at a kind of photonic cloaking effect, an ability of the structure inside 3I Atlas to control its visible signature by modulating how light exited its surface. Imagine a surface so finely tuned it could adjust its optical appearance based on angle, distance, or time of day. Not with mirrors, but with something far more advanced, something alive to light itself. The next red flag came from polarization data. Normally, sunlight that reflects off a dusty object gets polarized in predictable ways. But here, the polarization was rotating, not consistently, not like it was spinning. It was rotating relative to the observer, depending on where Earth was in its orbit. In simpler terms, it was tracking us. The light didn't just bend, it responded. This realization sent a ripple through the remote sensing community, because if the structure inside 3I Atlas was interacting with light in this manner, it wasn't just visible, it was communicating. Or worse, it was masking, changing its appearance at will, making us see what it wanted us to see, and nothing more. When the European Southern Observatory quietly tried to verify the same data using ground-based telescopes, they ran into something even stranger. Their light curves were inconsistent, jumping subtly from night to night, even when controlling for atmosphere and telescope calibration. It was as if the structure's internal dynamics were shifting, not randomly, but in cycles, almost like a sequence of optical commands, blinking on and off across a massive internal surface. By this point, nobody was using the word comet anymore, not internally. The internal briefing memos began to describe the object as a light-influencing structure embedded within a broader particulate envelope, a kind of shell wrapped in gas and debris, shielding a core that knew how to see and how to respond. The implications were staggering. If this thing could control what we saw, then what were we missing? Because in space, everything we know, distance, motion, temperature, composition, it all begins with light. And for the first time in modern astronomical history, that light was being played with, not by distortion, but by design. The question no one wanted to ask out loud was simple. What else could it be doing with the light we haven't noticed yet? When Hubble focused deeper into the structure, pushing the limits of light resolution and processing algorithms, it uncovered something even more unsettling. The structure wasn't centered. It wasn't symmetrical. One entire side of it appeared to taper off unnaturally, as if sliced or abruptly terminated mid-formation. That's when researchers began referring to it as the edge, and not just any edge, but the edge of what might be 3I Atlas's internal core. This raised immediate concerns because most known cometary or interstellar bodies that possess any form of internal structure are uniformly encased in icy or dusty shells. They erode gradually. They don't present sharp boundaries or geometric partitions. Yet here, deep within the faint haze of the comet's central mass, there was a visible contrast between what appeared to be a dense, angular surface and a surrounding void of near-total darkness. It was almost architectural. Initial data suggested the edge wasn't natural. There was no smooth gradient, no sign of chemical decay or fracturing. Instead, it looked imposed, as though whatever this structure was, it had been deliberately bounded, cut off, possibly, or left incomplete. And that prompted a series of questions that shook the mission teams. What kind of force could slice an object inside an interstellar body with such clean lines? Was this the aftermath of a cosmic collision, a remnant of a failed propulsion system? Or worse, was it by design? Scientists fed the imagery through a host of spectral and thermal models, hoping to find inconsistencies that could be chalked up to illusion, pixel noise, refraction, gravitational distortion from nearby bodies. But each attempt only confirmed the same thing. The edge was real. It held its line across varying imaging passes and across several rotational shifts of 3i Atlas. No matter the angle, that abrupt boundary persisted, and then came the more worrying observations. As 3i Atlas rotated, and it was rotating faster now as confirmed by light curve analysis, this edge would briefly become visible to Earth-based instruments as well, and each time it did, something strange would happen to nearby solar radiation readings. A dip, a drop in certain magnetic field harmonics. Instruments from different agencies picked it up too. Subtle, but measurable shifts in radiation pressure when the edge was facing Earth. That wasn't supposed to happen, because it implied that this structure wasn't just passive. It was doing something, affecting space itself, not dramatically, but enough to bend or absorb certain waves. And if that was true, then the edge wasn't merely a boundary. It might be an interface, a functional layer, possibly a shield, or a boundary to an inner chamber that had yet to be revealed. A theory emerged that changed the entire tone of the Hubble session logs. What if this structure was intentionally hidden inside the comet, only revealing itself now because of erosion, heat exposure, or internal activation? In that case, what we were seeing wasn't a fluke of trajectory or light. It was a glimpse at something that wasn't meant to be seen. And still, no one could explain why a comet, especially one on an interstellar trajectory, would house something like this. The timeline didn't fit any known planetary system. The energy distribution didn't align with any natural comet decay. And now, with the edge clearly visible and affecting measurements across solar instruments, the scientific community found itself split into two camps. One believed we were witnessing the remains of an ancient alien probe, decaying silently as it passed through the solar system. The other believed it was still operational. Neither camp could explain the final anomaly from the edge. Because for just over 40 seconds, during its latest close pass, Hubble picked up what looked like movement inside the boundary, and that movement wasn't tumbling like ice, it was rotating smoothly. As if guided by some internal system that was just beginning to wake up, it began as a flicker, not of light, but of order, of symmetry hidden in the chaos. When Hubble's enhanced spectral filters were layered over the structure's central mass, a pattern began to emerge. At first, astronomers dismissed it as a compression artifact, something caused by signal interference, data loss, or the usual digital hiccups that come with long-range imaging. But when they cross-referenced it with secondary scans from infrared and X-ray overlays, the same pattern reappeared, layer after layer, and it wasn't noise, it was intentional. Right at the center of 3i Atlas, beneath the jagged structures, the shifting fields, and the oddly translucent segments, was a lattice, but not just any lattice. This one repeated at intervals that didn't make sense for ice or rock. Its geometry was unnaturally clean, forming interlocked segments that twisted slightly with each layer, almost like a spiral shell caught halfway through a metamorphosis. It looked crystalline, but not like any mineral ever catalogued. What made it more baffling was its reaction to light. When certain spectrums of UV radiation hit the structure, parts of it became briefly reflective, almost iridescent, creating flashes of coherent reflection, like a mirrored pulse aimed outward. But that pulse didn't just scatter randomly. Observatories tracking the refracted signal noticed it consistently aligned with specific star groupings. And more unsettling, those groupings changed depending on 3i Atlas's position relative to Earth. It was almost as if the object was recalibrating the direction of its response. Several astrophysicists at the time proposed that this pattern was nothing more than an extremely rare form of pressure-forged crystalline water locked in phase from deep space collisions. But others weren't so sure. The structure wasn't behaving like a passive mineral. it was reacting. NASA's internal panel, typically cautious in its wording, began referring to this inner region as the core matrix, and while they didn't go so far as to label it artificial, they did note that the symmetry was highly anomalous for known cometary cores. One expert described it as architecture without a blueprint, a natural form that looked built but not by human hands, or perhaps not by hands at all. And this wasn't the only strange thing. The crystalline pattern had an energy shadow. Instruments on Earth picked up faint EM echoes bouncing off the core matrix, oscillating in low-frequency bands that pulsed with a regular rhythm. One pulse every 3.7 seconds. Like a breath. Not constant, but patterned. Not mechanical, but alive in its timing. When they filtered those echoes through a magnetic waveform model, the shape of the echo resembled something from decades earlier. An old SETI transmission that was dismissed as a cosmic anomaly. The match wasn't perfect, but the rhythm was eerily close. Too close to ignore. That's when theories began to spiral. Was this matrix a signal receiver, a passive reflector, or something even more active? Something that was waiting to be triggered? The crystalline pattern didn't match any Earth-based structure, but it also didn't behave like a naturally evolved one either. Whatever it was, it sat at the heart of 3 Atlas like a fossil frozen in time, preserved in layers of ice, dust, and electromagnetic chaos. It didn't look dead. It didn't look dormant. It looked suspended. Not decayed, but paused. And as 3I Atlas continued its slow arc near Earth, passing through magnetotail regions and interacting with our solar plasma in strange wave-like pulses, that crystalline pattern stayed visible, unchanged, unmoved, but somehow watching. Or maybe remembering. Because nothing in space is truly random. And this structure, more than any other part of 3I Atlas, seemed to be designed to endure, to wait, and perhaps, if the right signal arrived, to awaken. What troubled researchers most wasn't just the size of the structure within 3I Atlas. It was its symmetry. Hubble's deep-field composite images didn't merely show a mass. They revealed a network, something that appeared almost crystalline, with radial lines branching out from a central point and repeating at precise angles. The structure had order, and in space, especially within a fast-moving chaotic body like a comet, that kind of architectural symmetry simply doesn't happen by accident. On Earth, symmetrical geometry often signals intentional design. From the molecular scaffolding of engineered materials to the load-bearing trusses of suspension bridges, symmetry is the fingerprint of purpose. In the natural world, symmetrical patterns emerge too, spirals in shells, fractals in snowflakes, but never with this kind of rigidity, never deep inside a tumbling icy rock from interstellar space. Astrophysicist Dr. Kieran Halley from Caltech offered a sobering analogy during a press briefing. Imagine cracking open a geode and finding not crystals, but a perfect microdome with beams, arcs, and repeating pentagonal nodes. Now imagine that dome isn't growing, but holding together under pressure, near heat, and amidst volatile outgassing. That was what they were seeing inside 3I Atlas. The structure didn't appear fractured or warped, despite the violent stresses this comet had undergone. After surviving a brutal perihelion close pass with the Sun, parts of its outer layers had blistered and burst. Yet the internal structure remained intact, unbothered, and as Hubble's follow-up images showed, still visible through breaks in the outer crust. At first, some assumed it was an optical illusion, a visual artifact from image stacking, or perhaps the result of overlapping reflections off ice lenses. But independent observatories across the globe, from Chile's Atacama Desert to Antarctica's Dome Sea, soon verified the pattern, and the more telescopes joined in, the more impossible it became to dismiss. What looked like symmetry wasn't a trick, it was real. The pattern repeated on multiple axes, it rotated in alignment with the core's spin, which meant it wasn't just a shell but embedded deep within the mass. That ruled out the possibility of a surface feature or a trick of illumination. This wasn't caused by ice fractals or accidental deposition. It was something else. The question that began to haunt researchers was this: why would any structure, natural or otherwise, form with this kind of precision inside an object never meant to last? Comets, especially interstellar ones, are usually transient. Cosmic nomads that burn, break or fragment as they pass close to stars. They're not stable, they're not protected, and they're certainly not preserved. Yet inside this volatile projectile was a geometry that had survived. Dr. Halley wasn't alone in raising the alarm. Dr. Aziza Malik, an astrophysicist from the University of Geneva, published a short paper titled Symmetry and Chaos, the Anomaly of 3I Atlas, where she explored the possibility of engineered metastability. She proposed that the structure inside the comet could be a result of self-assembling systems, nanoscopic or lattice-bound clusters that could withstand violent thermal shifts. That hypothesis opened a new door, because if something inside 3I Atlas was self-assembled, it might also be self-aware, or at the very least, self-regulating. It was then that the team began running simulations, not just of the object's trajectory, but of what could form such a symmetric lattice inside a spinning, unstable mass. The results were unsettling. The only scenarios that preserved symmetry under stress involved feedback loops, mechanisms that adjusted in real time, internal structures that resisted disorder, not through mass, but through information. Meaning this might not be a structure at all, it might be a system, and that was worse, because a system adapts, a system responds, and if 3I Atlas contained such a system, then it wasn't just a comet, it was a container, or a traveller, or something else entirely. When Hubble's ultra-sensitive photometry was run through the latest motion-corrected data stacks, something strange emerged, again. This time, it wasn't a glow or a shadow, it was a ripple, a gravitational one, not enough to cause orbital displacement, but enough to bend starlight, enough to warp nearby plasma in measurable ways, and enough to cause theoretical physicists to sit up straight in their chairs. Normally, cometary bodies like 3I Atlas don't have the mass, or the internal consistency, to create any noticeable gravitational distortions. They're loose collections of dust, ice, and rock, dirty snowballs drifting through the vacuum. But this anomaly didn't behave like dust or gas. It behaved like something dense, something with weight, and it was moving with precision. As light from background stars passed behind the structure now seen inside the comet, it bent in a way that suggested localized gravitational curvature. This bending wasn't constant. It pulsed, slightly, but predictably, implying that the mass itself was shifting, as if rotating or modulating, not random, structured. Hubble's data was sent to several gravitational observatories, including ESA's Gaia mission and a small high-altitude lab in the Chilean Andes with custom optical gear. Preliminary results were uncomfortable. They matched. The distortions weren't observational errors. Multiple sources confirmed that 3I Atlas, more precisely the mass inside it, was creating real gravitational anomalies measurable from Earth orbit. What made it worse was the location. These distortions weren't at the surface or edge of the comet. They were coming from the core, deep inside the structure that Hubble had visually mapped. The same core that had previously pulsed with unknown heat and light. Now, it appeared to be generating its own gravity signature. Not in the classical sense, there was no mass large enough to explain it, but in a dynamic, non-uniform sense, a gravitational ripple that flexed with time. Astrophysicist Dr. Nima Tagore, a leading specialist in exogravitational lensing, made an offhand comment in her lab notes that later circulated widely. We're not looking at a mass, we're looking at a behaviour. Something is generating synthetic mass signature. This may not be a comet anymore. The phrase synthetic mass signature caught fire. Reddit threads exploded. Theoretical papers rushed to Arxiv, and in private, the panel advising the European Space Agency on 3 Atlas met in emergency session. Because synthetic mass implies intent. It implies engineering. Now, theories diverged sharply. Some believed the object was producing gravitational waves in order to navigate, like a dolphin using sonar but through space-time. Others argued it might be a defense mechanism. Still others whispered about gravitational memory structures, hypothetical constructs designed to interact with mass in specific historical contexts. But all shared one central fear, that we were observing something built, not formed. Something tuned to the fabric of gravity itself. And gravity, unlike light or heat, is not easy to fake. It is fundamental, unforgiving, and visible across vast distances when disrupted. The only other known case of an object producing gravitational lensing without sufficient mass was the infamous case of the Oumuamua-like anomaly that passed Jupiter's orbit in 2032, an event still officially classified. But this was different. This time we had images, we had distortions, we had a timeline, and the clock was ticking, because the ripples weren't fading, they were increasing, daily, which meant either the object was spinning faster, compressing, or becoming more active. And if it was active, what was it doing? At the Jet Propulsion Laboratory, a senior systems analyst left a single comment in the 3I Atlas anomaly tracker log. No comet has ever behaved like this. That's not gravitational echo, that's a beacon. A beacon. That idea returned again and again. Not just movement, but message. Not just mass, but intention. And if 3I Atlas was emitting gravitational signals to someone or something, the real question wasn't what we were seeing, it was who else was supposed to see it? When astronomers examine structures in space, it's not just about what they see, it's about what those structures do over time. Motion reveals intent, changes tell stories. That's why, after Hubble's imaging team first confirmed the existence of the strange structure inside 3I Atlas, their next step was to map it not just in shape, but in behaviour. The images had already shown something unusual, something that wasn't natural. A skeletal lattice embedded within the coma of the interstellar object, reflecting light differently than any nearby dust or gas. It pulsed in a way that defied known explanations. But when the team overlaid sequential frames, something even stranger emerged. The structure wasn't stationary, not in the usual drifting sense of a tumbling cometary core, or the natural procession of dust as it's dragged by solar radiation. This was a coordinated shift. The internal scaffolding appeared to reconfigure slightly frame by frame, over an interval of about 46 minutes. Not a rotation, not expansion, but realignment, sections sliding into new geometries. And then, something even more provocative, the realignment formed a repeating sequence. Every 46 minutes, the structure returned to its starting configuration, then began the same transformation again. Like a mechanical bloom cycling through a preset loop, like a gear engaging unseen machinery. There was no external force that could reasonably account for such a rhythm. Not Jupiter's pull, not solar wind, not impact pressure from trailing particles. This was self-directed motion. A deeper analysis of the pattern revealed 6 unique configurations, each one distinct like frames in a looped animation. But that's not what made scientists sit up straighter in their chairs. What made the sequence so unnerving was the symmetry between those frames. They weren't just random shifts. They followed a geometric principle, one observed in terrestrial engineering, modular symmetry. On Earth, such symmetrical reconfigurations are seen in robotics, in antenna arrays, in objects that are meant to transmit or receive information across different vectors. It's how satellites align phased arrays. It's how deep-sea sonar equipment maintains signal strength across turbulent currents. It's not a natural phenomenon, it's a design language. Dr. Rafika Al-Kamil, a systems engineer brought in from the European Space Agency, described the pattern as non-organic, non-random, and likely functional. She stopped short of calling it intelligent, but only just. If this were a terrestrial object, we'd classify it as a dynamic sensor grid, but because it's embedded inside a comet from outside our solar system, we're still searching for other explanations. But those explanations are running out. Some astronomers proposed it could be an artifact of light refraction, an illusion caused by overlapping ice crystals or refractive dust shells. But that theory collapsed when infrared scans showed consistent thermal shadows during each reconfiguration. The object wasn't just appearing to shift, it was absorbing and re-emitting energy differently in each stage. That means its geometry was really changing. Others suggested magnetic interactions. Perhaps 3I Atlas had a strong internal magnetic field causing crystalline structures to align, but measurements didn't support that either. The magnetic footprint of the object was weak, barely above background solar levels. What remained was a mystery that didn't like being reduced. When NASA's Jet Propulsion Laboratory plotted the 6 configurations on a 3D axis, they found something else. The final state in the cycle pointed toward Earth. Not directly, not as a signal, but as an alignment, like the petal of a dish opening toward a station. Was it coincidence? Alignment bias? or was it time for a new kind of question? The object wasn't just tumbling through space, it was cycling. Predictably, deliberately, and its final orientation in each cycle wasn't random, it was Earth-facing. As the Hubble telescope continued its scan of 3I Atlas's bizarre internal structure, a new observation surfaced, one that demanded recalibration of the entire mission's data models. The anomaly wasn't just a centralized void or a mirrored layout, it had directionality, a strong axial signature. One end of the object, aligned along a calculated vector, was subtly brighter, emitting a structured band of reflected solar radiation that shimmered in a way Hubble's optics weren't used to seeing. The other end was dimmer, less defined, as if obscured by microdust or a cloaking field. That asymmetry, directional imbalance in brightness and spectral activity, suggested something that sent every analyst into a frenzy: intentional displacement, an axis, a deliberate orientation. In natural comets or celestial bodies, such directionality usually corresponds to rotation, sunlight exposure, or tail alignment. But this wasn't that. The tail wasn't trailing the brighter side. In fact, the antitail was skewed in a way that contradicted solar windflow models. It was as though the structure inside 3I Atlas had repositioned itself to face something. It had an active front and a passive rear, and when simulations were run, mapping the orientation of the internal structure against the solar system's star field, something astonishing emerged. The brighter side of the anomaly was angled almost perfectly toward the ecliptic plane, aligning with Earth's orbital path within a margin of 0.04 degrees. That level of precision was uncanny. No tumbling asteroid or passive icy body drifts into such exacting position by chance. And yet, the data was holding. Over multiple days, Hubble confirmed no observable rotation of the structure's axis. Whatever this object inside 3I Atlas was, it had locked itself into place. It was maintaining a stable directional bias, even as the comet's outer shell continued its natural momentum. That created a paradox. How could something inside a fast-moving, decelerating object maintain internal angular control without showing spin or reaction on the outer shell? The answer was either an internal counterbalance system or something more advanced, an inertial anchoring mechanism. Astrophysicist Dr. René Holtz, who had studied exoplanetary magnetodynamics, was among the first to publicly question whether this directional bias was responding to gravitational cues or to electromagnetic ones. Her paper, rushed into peer review under the title Inertial Lock or Intentional Pointing, introduced a hypothesis that shook even hardened skeptics. The structure inside 3I Atlas might be using the Sun's magnetic field, not as propulsion, but as navigation, like a spacecraft tuning into a magnetic lane. That would imply not only awareness of the heliospheric layout, but pre-mapping of its flow corridors. Other scientists took it further. If the anomaly had directionality, and it pointed near the Earth's ecliptic, could it be mapping us? Was it gathering alignment data for a potential future pass-by? Or worse, for relay positioning? The idea that the object might not only be observing but preparing a network was no longer speculative fiction. It was a line of inquiry. What added weight to this theory was that the brightest limb, the head, as some dubbed it, was not just reflecting sunlight. It was pulsing. A rhythmic, low-frequency modulation at near-infrared wavelengths had been detected by both Hubble and a ground-based infrared array in Chile. The pulse was slow, 1 every 37 minutes, but it was stable, and unlike any albedo fluctuation caused by dust or rotation, it had a waveform. It suggested a clock or a beacon. As the astronomy community held breath, cross-checks with Voyager and SOHO showed no matching pulses in the deep background, yet. But attention was now sharply focused. Because if this axis wasn't just a passive quirk, if it was a pointing device, then 3I Atlas wasn't just on a path, it was aiming. In the realm of deep space observation, every unexpected deviation is met not with panic but with protocol. When the Hubble team noticed a faint, almost imperceptible smearing of background starlight behind the center of 3I Atlas, their first assumption was instrumental, that something within the telescope's optics or a transient vibration in the mirrors might have skewed the light path. But this wasn't an artifact. It was persistent, repeatable, and it pointed to something far more compelling: gravitational lensing. Lensing occurs when an object's gravity bends the light from sources behind it, much like how a magnifying glass curves and focuses light. It's one of the more dramatic predictions of general relativity, and one of the most useful. It has allowed astronomers to map dark matter, observe the curvature of space-time, and even peer deeper into the cosmos than would otherwise be possible. But in this case, something felt off. This wasn't the clean, symmetrical arc you'd expect from a uniform gravitational field. It was jagged, asymmetric, almost sculpted. What made this event especially curious was its location. The lensing wasn't happening at the comet's surface or around its perimeter. It was centered, aligned precisely with what Hubble had initially flagged as the densest part of 3I Atlas's nucleus. But unlike typical gravitational lenses, which require massive, compact objects like stars or galaxies to warp spacetime, this one seemed to originate from something much smaller, yet strangely more intense. A second scan, cross-referenced with James Webb's infrared sensors, showed a sudden, sharp drop in photon transmission just behind the nucleus. This blackout wasn't due to opacity. It wasn't that something was blocking the light, like dust or gas, but rather that the light itself was bending unnaturally as it passed through the region. It was as if the core was surrounded by a tightly folded pocket of spacetime, one that neither matched the comet's observable mass nor adhered to Newtonian expectations. When physicists ran the numbers, the data suggested a gravitational pull several orders of magnitude too strong for a comet of its known size and density. The core was either harbouring something extremely dense, like a collapsed object, or exhibiting a mass signature that was being artificially amplified. Neither outcome fit into the current models of interstellar comets, and that's when the term core shadow lensing entered the lexicon. It was coined by a postdoc reviewing the Hubble data overnight. Her metaphor was simple. If typical gravitational lensing is like a clear glass sphere bending light in smooth curves, then this was more like a cracked lens, full of warps, splinters, and internal prisms, not destructive, but uneven, fragmented, almost like it had been designed to bend light around certain internal geometries while obscuring others. The implications were massive. For one, it suggested that whatever was at the centre of 3I Atlas wasn't just dense, it was spatially complex, possibly hollowed, possibly active, possibly structured, and that meant 3I Atlas wasn't just a passive object careening through space, it was interacting with space-time at a level no natural body of its size had ever demonstrated. Even more intriguing was the realization that these distortions were angle-specific. Depending on Hubble's viewing perspective, some lensing effects intensified while others vanished entirely. That meant the object at the core wasn't a uniform mass. It had faces, edges, perhaps compartments. At NASA's Jet Propulsion Laboratory, models began to simulate what kind of internal structure could produce such warped light patterns. What emerged weren't spherical cores or solid rocks, but lattice-like designs, grids, hollow chambers with reinforced struts, akin to the truss systems used in satellites or orbital stations. The analogy was deeply uncomfortable, not because it was conclusive, but because it echoed something engineered. For now, the term remains theoretical, but the data is real. Something inside 3I Atlas is bending light, not with the slow, soft pull of a dusty comet, but with the focused intensity of something dense, internal, and sharply defined. And that's not just an optical anomaly, that's a clue. As astronomers pored over the Hubble data revealing the structure inside 3I Atlas, a parallel effort began to take shape. Scientists realized that to make sense of this newly uncovered anomaly, they had to cross-reference it against something familiar, something that had seen the edges of the solar system and survived. That meant Voyager 1 and Voyager 2, the twin probes launched in the late 1970s, now drifting through interstellar space, transmitting faint signals across the cold dark. At first glance, this might seem like an odd pairing, an ancient probe and a hypermodern telescope. But Voyager's long trek beyond the heliopause, the boundary where the sun's influence wanes, had already recorded strange energy fields, drops in cosmic radiation, and directional anomalies that many had written off as noise or sensor degradation. But with the new findings from Hubble, those old readings suddenly took on a sharper focus. One particular transmission from Voyager 2, logged on August 19, 2025, described an abrupt spike in magnetotail distortion just before its long-range instruments fell silent for a brief window. At the time, it had seemed like an ordinary background event. Now, researchers began to ask, what if Voyager had briefly passed through a fringe or projection of the structure now visible inside 3I Atlas? Comparing the magnetic field lines modelled from Hubble's light refraction data with archived Voyager telemetry showed something unexpected. The structural orientation of the object within 3I Atlas had field alignments that loosely mimicked those recorded by Voyager 2, down to the pitch and curvature of the surrounding plasma interactions. It was as if both had encountered similar spatial distortions, spaced years apart and at vastly different locations. This revelation triggered a new wave of simulation, using data from both the Hubble analysis and Voyager's telemetry. A team at Caltech fed parameters into a dynamic 3D model to reconstruct a theoretical lattice, what some were now calling a gravitational harmonizer, capable of warping local space without collapsing under its own mass. If correct, this would suggest the structure inside 3I Atlas wasn't passive, it was active, engineered, a kind of long-term stabilizer or energy modulator. But this idea brought even more uncomfortable questions. If Voyager had interacted with a similar structure years before, why hadn't we noticed sooner? Had the anomaly gone dormant, or had it simply been hiding in plain sight, undetectable until a more significant cosmic shift like the arrival of 3I Atlas triggered it? One quiet voice in the room, a senior researcher who had worked on the original Voyager team, noted something chilling. He recalled how in 2019 the probe had experienced a momentary loss in signal fidelity, as if something had refracted its transmission back upon itself. At the time, they assumed hardware aging was to blame, but now, paired with the reflective geometry seen inside the comet, that disruption resembled a bounce, a mirror echo, as if something out there had listened and replied. Cross-referencing deepened. Archival pulses from Voyager were reanalyzed. Patterns thought to be cosmic ray interference were reclassified as potentially phased returns, delays in bounce back that could signify an intervening structure. With every overlay, more alignment emerged, and perhaps most shocking of all, the directionality of the object's internal struts, as revealed by Hubble's multi-filter exposure stack, seemed to follow not a random path, but a vector, one that traced backward, not from the Sun or Earth, but from the current location of Voyager 2. Was the structure aligned toward the only active human-made object beyond the heliopause? Had it been placed there to see Voyager? If so, the implications were staggering, because it meant the object wasn't just situated inside 3I Atlas by accident. It might have been watching, or waiting for us to look back. And now that we had, it was no longer silent. As the Hubble data streamed in, another anomaly emerged, one that sent an unexpected ripple across the global scientific community. It wasn't just the light signatures or the unexpected contours inside 3I Atlas that baffled researchers. It was something far subtler, yet far more consequential. A wave of magnetic reverberations that seemed to emanate from the comet itself. Initially detected by the solar and heliospheric observatories, SOHO onboard magnetometers, the signal was faint but consistent. Oscillations in the interplanetary magnetic field that corresponded almost perfectly with Hubble's imaging timestamps. Each time a particularly dense cluster within the 3I Atlas interior was captured on camera, SOHO recorded a corresponding deviation in the magnetic field lines passing through its observational corridor. At first, it was written off as instrument noise, but that assumption didn't hold up for long. The frequency of the reverberations matched nothing in the known solar spectrum. It didn't align with solar wind behavior, nor with heliospheric disturbances typically caused by passing CMEs. Instead, the pattern mirrored something akin to a controlled pulse, deliberate, structured, and consistent in amplitude and frequency across an extended range of detection arrays. This wasn't chaos. It was a signal, a pulse, a heartbeat. Teams at NASA's Goddard Space Flight Center ran simulations comparing the magnetic signature with known cometary magnetic fields, such as those recorded during the Rosetta mission to Comet 67P. The difference was staggering. Most comets produce erratic, low-amplitude signatures, more a byproduct of outgassing and surface ionization than any internal magnetic order. But 3I Atlas behaved differently. It pulsed in triplets. The spacing between each pulse was exact, down to the millisecond, suggesting either an incredibly stable natural process or something engineered. Meanwhile, in Japan, the Kagura Gravitational Wave Observatory began picking up something it hadn't expected. While designed to detect distortions in spacetime caused by cosmic collisions, Kagura's highly sensitive interferometers registered localized perturbations during key Hubble observation windows. Though far below threshold for gravitational wave confirmation, these tiny oscillations hinted at a more complex interaction occurring around the object, perhaps a transient distortion field or magneto, acoustic pressure wave radiating outward from the core. Theorists scrambled to provide models that could account for the data. One proposed a superconducting loop buried inside the comet, a natural toroidal formation that had somehow retained an amplified magnetic flux from past solar encounters. But this ran counter to established understanding. Comets aren't made of materials conducive to superconductivity. Another theory floated the possibility of a magnetic cavity, an internal void structured in such a way that it traps solar magnetism and then releases it in synchronized bursts as the object rotates. But again, the observed regularity of the signal didn't match known natural harmonics. The wildest theories came from outside conventional astrophysics. One team at a European institute suggested that 3i Atlas might be interacting with a form of non-visible energy, perhaps a relic field from another star system, encoded into its core during interstellar travel. This idea, while speculative, was given a cautious review due to the sheer strangeness of the data. If the comet had passed through environments unknown to us, could it have accumulated exotic energies now slowly discharging into our solar magnetic fabric? Back at Hubble's control center, analysts overlaid the magnetic pulse data with their visual mapping. A pattern emerged. The interior structure, particularly the honeycomb-like layers and the central shaft of reflective material, appeared to glow more intensely during peak magnetic discharge. Could it be resonating in response to those emissions? Was this comet emitting energy intentionally, or simply reacting to the sun in a way we've never seen? The implications grew heavier with each confirmed observation. We were no longer looking at a passive object moving silently through the solar system. 3i Atlas was interacting, resonating, perhaps even responding. And as its trajectory brought it closer to Earth's magnetic footprint, the question arose, would we feel these reverberations directly, not as data, but as force? The initial shock of discovering a massive structured form inside 3i Atlas was already enough to jolt most astrophysical models. But what came next wasn't just surprising, it was paradigm-shifting. Upon enhanced examination of the layered intensity readings from Hubble's most recent high dynamic range pass, something emerged that even seasoned NASA analysts had to rerun twice. Inside the larger structure, already abnormal due to its linearity and internal reflection symmetry, there appeared to be a substructure, smaller, nested geometries, with boundaries, with movement. And that's when it all changed. The substructure didn't appear to be a natural density pocket or a random clumping of debris. It exhibited symmetry on a smaller scale, suggesting some form of modular or recursive design. Imagine unfolding a Matryoshka doll in space, not once, but multiple times. The outer shell of the anomaly, already tightly packed and impossibly aligned, now revealed secondary layers that obeyed their own gravitational logic, resisting the centrifugal forces one would expect from a tumbling mass moving at thousands of kilometers per second. NASA's Jet Propulsion Laboratory began applying fractal analysis to the Hubble light curve fluctuations, and what they found was staggering. The echo patterns from light bouncing within the substructure produced harmonic intervals, not unlike the harmonic spacing found in engineered antennas or resonant chambers. These weren't just visual oddities, they were mathematically consistent and repeatable. Suddenly, the question wasn't just what the structure was, it was whether it had intentional design. Meanwhile, the European Space Agency's Gaia Observatory attempted to cross-reference the observed rotation wobble from 3i Atlas with known cometary drift patterns. It failed. None matched. Instead of the irregular tumble expected from an icy object under solar torque, 3i Atlas exhibited axial stability, as if some hidden mass deep within was acting as a gyroscope. And then came the more chilling question, was this thing adjusting itself? Comparing time-stamped imaging from the previous 48 hours, scientists noticed micro-adjustments in the angle of the substructure, shifts as small as 0.2 degrees, but significant enough to affect reflection of solar radiation. At that distance and scale, such realignment wasn't something gravity alone could explain, nor could outgassing pressure. These movements were precise, synchronized, and, perhaps most disturbingly, predictive. One astrophysicist described it as watching a flower open under sunlight, except the petals were aligned to thermal gradients instead of light. That analogy spread across the Slack channels of several space agencies, sparking debate over what was now being referred to as the bloom effect. But if the object was blooming, it meant one terrifying thing: the substructure was responsive. Elsewhere, Deep Space Network antennas picked up faint polarization shifts in the returning Hubble telemetry. While still under analysis, some believe these shifts indicate that light passing through the substructure is being altered, not just scattered, but phase-shifted. This raises the possibility that 3 Atlas is not merely reflecting light, but manipulating it, bending it along internal corridors like fiber optics. That hypothesis would make the substructure a guidance system, one capable of rerouting incoming energy for reasons unknown. Was it defensive, propulsive, communicative? At this point, speculation within the inner circles of the astrophysics community became unavoidable. There were whispers, mostly off record, about this being the first case of interstellar architecture, something that was built, shaped, nested intentionally. And the scariest part? The object was still heading in Earth's general direction. The implications of that trajectory, combined with a nested moving substructure and harmonic signatures, ignited an emergency rebriefing at both NASA and ESA. Because if this wasn't just a random cosmic curiosity, then it may be the most calculated arrival in human history. And the window to understand it was closing fast. When the signal first failed to return, no one panicked. Deep space communications have always been finicky, often hindered by solar interference, line-of-sight shifts, or simple system noise. But what made this moment different was the sheer silence that followed. The echo from 3I Atlas's region, the expected backscatter pulse from an active probe, never came. Not delayed, not distorted, just absent. The null echo sent immediate ripples through every space agency's data relay center. It was supposed to be a routine calibration check, a kind of sonar test across the solar system, a precisely timed pulse from Earthbound radar, aimed at a known position where Hubble had visually locked on 3I Atlas just hours earlier. But instead of receiving the expected bounce, the detectors recorded something eerie, a clean frequency gap, a void, as if something had swallowed the pulse mid-flight. Silence in space is not uncommon, but clean silence, perfectly timed, perfectly isolated, devoid of background scatter is rare. And in this case, it wasn't a sign of natural absorption or instrument failure. The system logs confirmed that adjacent satellites still registered interstellar noise. Mars relays picked up faint echoes from the same zone. Only the Earth-originating test signal seemed to vanish entirely, as if it had been intercepted, scrubbed, or redirected. Researchers at the European Space Agency were the first to flag the discrepancy publicly, releasing a statement that described the phenomenon as a highly unusual non-return signature from a known object's coordinates. NASA followed with its own internal alert, not to the public, but to affiliated research centres. It wasn't a call of alarm, not yet. But it was a directive to shift every deep space dish toward the coordinates of the last known position of 3I Atlas and listen, continuously, without interruption. It's here that the mood started to change, because listening didn't help. There was still no echo, no whisper of the signal that had been sent, no residual scatter off nearby dust or gas fields, just a stark, blank window in the data, an acoustic footprint of nothingness. And to the scientists who've spent careers mapping the behaviour of radio waves across the solar system, that kind of silence is the loudest alarm possible. One theory began circulating behind closed doors. What if the signal hadn't just been absorbed, but had been intentionally nullified? What if something at that location, something unseen, was capable of active suppression, not just of emissions, but of detection itself? It would imply a form of cloaking far beyond anything Earth had achieved. Not invisibility in the visual sense, but a silencing of echoes, of presence itself. The Hubble images taken before the signal test became even more vital. Analysts rescanned them with different filters, searching for any motion blur, any energy flare, any sign that 3I Atlas had changed position or expelled something capable of this disruption. One frame showed a faint crescent of diffused light, like a refracted halo. But it wasn't tied to the comet's nucleus. It floated several arcseconds off-center, detached but fixed.